Okay, Wang Chu, I did not bring it with me. I'll bring it to you next time. All right? No, sorry. Okay, I can start anytime. All right, good afternoon. We have finished, I think, the most important chapter in this course. That's chapter 5. It basically talks about several important things about advanced MOS transistors, mainly more accurate IV model and the problem of short channel devices. All right? Okay, short channel effect. So next, I want to remind you that if you look at the course syllabus, you should be reading well technology. So this will be the assigned reading. Now, if you are looking at the reader, the slides, you may notice that I have jumped quite a few lectures. I'm looking at the slides of lecture 20. And I think the ordering this way would be a little better, and I'll explain why later on. All right? And what we skipped are materials not covered in the textbook. I will still use the slides. It's just I will use them after I finish chapter 9. All right? Okay. So you should start read well technology. We will not discuss that in the lecture unless you have questions. Bring them to the lecture or discussion session. We'll talk about it. Today we'll start a new chapter called hot carrier effect. It's chapter 9. And perhaps just back a little bit. Don't particularly look at the word hot carrier effect, what that stands for. The chapter has to do with problems caused by the high electric field in the channel. And the electric field is not high throughout the channel. Mainly the electric field is high in this velocity saturation or pinch-off region. Right? There the electric field becomes very high, and as a result some problems arises. Now there are several problems that arise out of this high electric field. The one that's most of a concern is something that one may call device degradation or drift of IV. All right? And this diagram illustrates what that phenomena is about. Here we're looking at a simple ID versus VD plot. First look at these two solid lines. These are two representative ID-VD curves, in other words, for two different VGs, all right? Okay, just two of those, all right? IV curve. Now, this transistor, if you operate it for a while meaning many years, of course, under the normal operating condition VDD, or it's only a matter of minutes if you operate at higher VDD than the nominal voltage, right? Suppose it's a 3-volt part and you operate at 5-volt. Then you're going to see this happen just within a matter of minutes, perhaps hours. What's going to happen eventually is that the IV curve drifts. So that's why, therefore, this word drift of IV is another way to understand what we're talking about, all right? Now, usually, not usually, a particular concern is the kind of drift that lowers the device performance. For example, the current drifts to a lower current. And for that reason, we use the word device degradation. It implies becoming a worse device, all right? Now, there are some cases, not very often, the device characteristic would drift to, say, higher current and perhaps even higher performance. In that case, we still call it device degradation. You hear this term used. It really means a device drift of IV. Okay? This device becomes different from what it was or it is when you test it. You see, this is a reliability problem. Okay? Reliability in the sense that, the last thing before you ship a circuit, let's say a processor, to the customer, you should do something called a final test. And this is the final test that you determine, gee, indeed it meets the 1 gigahertz speed, right? So you sell it for that price. And then the customer build it around all the other parts chosen to meet with the spec and sell the computer for that speed. And if the transistor drifts, as indicated in this diagram, then the circuit will no longer function at 1 gigahertz. Is that right? Yeah? And that's a reliability problem. Okay? All right. So it's a speed loss. That's basically the concern. Now, there are other hot carrier problems. As I said, this is not the only problem that can be related to high field hot carrier. There are problems like device breakdown, device degradation is one, then the transistor breakdown is related to the same high field and the same kind of very similar origin. Impedance give you substrate current. Impedance meaning as the electrons, or holes for that matter, whatever carrier move between from the source to the drain, these carriers become energetic, and we call them hot carriers. When they're energetic, they're hot carriers. And these hot carriers create impact ionization. In this example of p-channel, n-channel transistor, impedance means electron-hole pairs are created. The new electron so created will just flow with the original electron into the drain, all right? And the hole so created will be pushed by the electric field. If you draw an energy band diagram, you will see will be pushed into the substrate, into the neutral region of the substrate. All right? There, it actually can flow, and if you have a contact to the substrate or well, whether in the back or in the front of the wafer, and if you put an ammeter in series with that contact to the substrate, you can actually measure the current flowing out of the substrate, and that's called a substrate current. So substrate current is a measure, or is a way to measure or monitor the rate of impact ionization. See what I'm saying? Generally, good approximation that all the holes created by impedance will be detected and collected in the substrate current. All right? Because electric field is such that holes will be pushed out into the neutral substrate and can be collected and measured by an ammeter. All right? That's called substrate current. Now, the substrate current, later we will see it's very useful thing. We're going to actually relate that substrate current to, for example, the device degradation, reliability, lifetime. Reason we want to relate all these things to substrate current is because among all these hot carrier phenomena, substrate current itself, substrate current is the only one that's very convenient to measure. Unlike device degradation, by definition, you have to wait for a while, right, to see what happens. Substrate current is not like that. You just, connect it to the ammeter, and you see substrate current. So it would be really nice if we can, for example, predict the device degradation lifetime based on the substrate current value, if possible, all right? Okay. But substrate current itself also causes other problems. You may or may not remember, we mentioned that impedance or substrate current actually cause the output resistance of a transistor to drop, the slope of this portion of the IV curve to increase. Yeah? That will affect the transistor gain, the voltage gain of the transistor. All right? So later we'll see again how this is related. We did go through that very briefly, how the substrate current create a bias between the substrate and the transistor due to the flow of the substrate current, and that bias causes VT to drop, and therefore our out decreases, right? The substrate current actually could also create enough body bias such that this source and body junction becomes forward bias at 0.6 or even 0.7 volt. At that kind of forward bias, electrons will actually be injected from the source into the substrate. Once electrons are injected into the base, it can simply diffuse to any other p-n junctions and other drains of neighboring transistors. Okay? And this will cause leakage current in the neighbors. This is known, for example, to, unless you take caution to guard against that, to reduce the refresh time of DRAMs, for example. This could be a problem. All right? And In a really a bad case, it can even cause latch up. But we talked about latch up, I think, last hour, the hour before. And we did say that today, latch up is not very serious a problem because design rules are very carefully fashioned and such that we really minimize the shunt resistance between the base and the emitter, the parasitic base and emitter, and to try to take the bipolar transistor out of commission, so to speak. And as a result of that, latch-up is not something we worry about every day. But if latch-up is a concern, turns out I-sub is one way that can trigger latch-up. Right? And another phenomena is this very energetic electron carriers actually can generate photons. And this could be due to the recombination hot carriers or just due to phenomena such as bremsstrahlung radiation that seems the more recent data support this just recombination of hot carriers so that you can have light coming out. And in fact, you can even get visible light coming out of this, all right? And we may or may not, maybe we'll have a chance to say a little bit more about this. I'll save a little more comments with this. So this is introduction, what's meant by hot carrier effect or high field effect. In a broad sense, you can use the term hot carrier effect to describe all these things. But in reality, when you hear people say hot carrier effect, you should assume that that term simply refers to device degradation. Simply refers to device degradation. All right? So perhaps you can use the term high field effect to describe all these things together. Maybe that's all right. This is together is called a high field effect. But the term hot carrier effect is reserved to describe the device degradation. Okay? All right. So how we're going to study this? We're going to break this problem into two parts. One part, the second part, is these different phenomena. The first part is we want to describe or review a model for the electric field in the channel, particularly the maximum electric field or peak electric field in the channel. The peak electric field in the channel, all right? We're going to try to understand this as function of, channel length, of course, but maybe also doping concentration, maybe a function of VG and VD and all these things, right? Okay. First, we want to understand what determines this electric field. Okay. Next, then we'll try to relate this electric field to at least these four different kind of high field effects. Is that right? Okay. And once we have done that, then you understand, for example, how breakdown, depends on channel length, doping concentration, oxide thickness, and VG perhaps, right? So we're going to divide the problem into two. First, we want to model this electric field as function of the physical parameters of the transistor as well as bias of the transistor. And then we're going to relate this electric field to these different effects. Okay? All right. So then let's look at section 9.1, the electric field. As I said, this is really kind of a review, but we'll do that. You remember that we have derived expression for the, let's just look at the second equation for now, for the potential in the high field region or pinch-off region. We did this to model the channel length modulation, if you remember. And this equation was derived in chapter 5, 565, all right? This electric field or voltage potential rises in the pinch-off region from the beginning of the pinch-off region here, let's say, rises kind of exponentially or according to hyperbolic sign until you reach VD, of course, at the end of the at the beginning of the drain, you get VD, and that equation is V minus VD set is equal to E set L prime hyperbolic sign Y prime over L prime. Remember that? Okay. Now we can rewrite that as hyperbolic sign Y prime over L prime is equal to V. Just rearrange this. Put a hyperbolic sign on the left-hand side. Then what we left is V minus VD set over E set times L. right, from the previous equation. Okay. Now, why do we want to do this? Because what we really are trying to do is we are trying to find expression for the electric field. All right. So now we'll back up now once. We'll back up this from the second equation back to the first equation. If we differentiate this expression for the electric field potential, we'll get expression for electric field. Ey prime is equal to Ez, we'll just differentiate this with respect to y prime. We'll get Ez hyperbolic cosine y prime over L prime. Is that right? Okay. Now, turns out we can rewrite hyperbolic cosine as square root of hyperbolic sine plus 1. That's the mathematical identity relationship between hyperbolic cosine and hyperbolic sine, right? Okay? Okay. Next, we're going to replace this hyperbolic sine function using this relationship. As a result, we can express electric field as function of V, not as function of Y. We really don't want it as function Y. We want to know function V, we'll see. And if you do that, turns out the result is this. E is equal to Ez, that same Ez here. That hyperbolic sine function is going to be replaced by this to the second power, right? There's second power. You see that? Yeah, plus 1. So what we'll put here is V minus Vd set over E set L prime. Yes? Square plus 1 is from plus 1. You see that? Okay, now why do we do that? We do that because all we want is to know the electric field at the drain where it's maximum. Is that right? We actually don't need to know the, well, let me tell you right now, we're not that interested in knowing, or we don't have to know the electric field at these points. We really want to know the electric field where it peaks. The reason is everything that we're going to talk about later on, such as impact and ionization rate, are very strong functions of electric field. So most of impact ionization is happening really near where the electric field profile peaks, right? Where it's 20% below the peak is really not that important, all right? Just because these high field effects are all such strong function of electric field, okay? All right, so we're going to try to get a handle on this maximum electric field. If all we want is electric field at the drain where it maximizes, then we just have to substitute the voltage at the drain here, and that's it. Is that right? And what's the voltage at drain? It's Vd, of course. It's okay? And once we decide to do that, we can further simplify this expression by realizing or approximating that this plus 1 is negligible. Okay? I can tell you this is a pretty good approximation, but you can always question whether it's still good with the future low power supply voltage. And certainly there's a lot of things you can do. Maybe you can consider re-examining a lot of approximations for your term paper, perhaps. Right? But typically this is a pretty good approximation, especially because it simplifies the equation. So we're going to do it, all right, just because it makes the mathematics simpler. So if we ignore this plus 1 term, which really means when EM is not very close to E set, many times larger than E set, right? Meaning this term is virtually larger than 1. So EM much larger than E set. Let me give you some numbers. Do you remember what E set is, typically? What's the value of E set, roughly speaking? E set is the electric field at which velocity saturates, right? Where velocity saturates. Velocity saturates at E set. So what is that E set? Do you remember? Okay, time 10 to the, okay.
2 times 8 times 10 to the 6 divided by saw 300.
Oh, I see. You use the saturation velocity divided mobility. That's very clever. All right. So I was really particularly looking for this exponent, right? If you remember it's volt per centimeter, then you're in the right ballpark. Okay. I probably would have called it 3 or 4. All right. 4 times 10 to the 4 is volt per centimeter. That will be in the right ballpark. Later you will see that all the problems due to high field effect start beginning important when we are maybe at larger than 2 times 10 to the 5, maybe more than that, maybe 4 times 10 to the E5. Sorry, let me do this. It happens at, say, larger than at least 3 10 to the 5 volt per centimeter. Okay? Below that, the electric field just does not wreak too much havoc. It's just when the field is large and we start to have problem, right? And so I'm just telling you, this is kind of the difference between the left-hand side and right-hand side. And therefore, this quantity must be, you know, almost factor of 10. Yeah? This means this quantity is probably a factor of 100, and therefore this 1 is typically negligible. It's okay? All right. So if we ignore this 1, then we end up with simply EM equal to VD minus VD set divided by L prime. That's it. You notice that? This E set cancels out, right? So we only have VD minus VD set over L prime. Okay? And provided this is the case, but I already showed you why this is a good approximation, because left-hand side, where we are interested in, is usually much larger than E set. Therefore, it's a good approximation. Okay? All right? Okay. And let's remind ourselves, what is L prime? L prime is that characteristic length for this exponential rise of the field, and approximately speaking, is square root of 3 Tox xj. I say approximate because analytical models always there are approximations involved, right? So let's just give us some handle. Turns out this quantity is related to Tox and xj. If Tox small or and xj is small, L prime will be small, right? Meaning the pinch-off region will be small. Okay? Now, in the case of channel length modulation, did we want small L prime or large L prime? Do you remember? If we want to minimize channel length modulation, we want a small L prime, because this pinch-off region length is proportional to L prime. Okay? In other words, thin oxide, shallow junction will give us transistor with very little channel length modulation. That's considered good from the performance of transistor. Now let's look at here. If your concern is high field effect, meaning you're trying to control the electric field, don't let that go to get too high, then do we want L prime to be large or small? Yeah. So this is a fundamental problem between the performance of the transistor and reliability of the transistor. So that's you here. When we scale the transistor, we're going to have more reliability concerns. Certainly this is a problem, right? We know that we want Tox to be small for many reasons, not just channel length modulation, short channel effect, we have seen that, and certainly ID set, we want that. But when we do that, those things, then electric field becomes large. Is that right? Okay, for any given VD minus VD set. Now fortunately, and perhaps by necessity, when we scale the transistor so much, we need to reduce VD. Okay? We have been reducing VD mainly because we want to reduce the power supply, or at least from the positive side is we'll reduce power supply. And indeed, there's another reason to reduce VD. It's well recognized. That is, for the kind of scaled transistor simply won't work at high VD because of reliability, right? Hot carrier reliability, we can see now one reason why that's the case. When you scale the device, you have to reduce these voltages, right? And oxide also breakdown. Oxide breakdown is another problem, which is a subject of another chapter. Okay. Any question about this model of the peak electric field in the channel? All right. Okay. So let's quickly review. What determines the electric field? What parameters has impact on the electric field? Does channel length have impact on electric field? Okay. I see some of you shaking your head, and I probably should not have asked you that as the first question. Turns out channel length has impact on the electric field. Why is that? As channel length gets smaller, VD set gets smaller. All right? It's for this reason electric field increases with channel length. Now you may say, well, that looks like a small effect. Actually, it's not a small effect, because hot carrier effect is strong functions of electric field. So electric field, if you increase by 20–30%, certainly can mean the difference between acceptable device or unacceptable device. Right? On the other hand, it's also true that your first reaction is also true, and that's very, very, it's a good knowledge. When you shake your head, is that EM is definitely not inversely proportional 1/L. All right. If you read a lot of these technology projection papers, you will see this kind of relationship bantered around, very freely. but it's definitely incorrect, all right? It's not such a strong function of channel length, right? See that, right? It's not that strong, and even not that strong a dependence turns out to be very important. Okay? So the L dependence comes through this VD set term, okay? And certainly it's function of VD. That's why we always have some kind of maximum power supply voltage transistor can apply at, all right? And what else does it depend on? It depends on oxide thickness, depends on the junction depths. You may ask, well, does it depend on the doping concentration? Now, according to this particular model, to the first order junction doping concentration, substrate doping concentration is not as strong a factor as these factors highlighted. Does that really mean that the doping concentration doesn't have any effect? It's not true either, because when we look at this quasi two-dimensional Poisson equation, Gauss box, we always argue that where we draw that box is somewhat debatable. Right? We drew the box at junction depths, but we think maybe doping concentration or X effective could have still some impact, right? Maybe. But we just don't think it's as strong effect as this. There's another reason doping concentration has impact, turns out. It has to do with, well, let's just try this. Suppose I increase N sub. What does that do? Well, first, it causes, if N sub increases, this will cause VT to increase, right, if nothing else changes. And this will cause VD set to decrease. Why? Because VD set, if you use the common model, becomes VG minus VT. Is that right? And this will then also cause electric field to increase. So general trend is true that you increase doping concentration, electric field will increase some. But what this model is telling us, and that usually surprises people, is that the doping concentration is not as strong an effect as one may think. Because a lot of people like to think about this what happens in pinch-off region like a one-dimensional p-n junction. They like to think that. For example, they like to use one-dimensional p-n junctions depletion region width to model the channel length modulation. Okay, we've already seen how different the problem is from one-dimensional p-n junction. Similarly, when they think that way, they will say, well, the electric field then must be a strong function of the doping concentration, because in p-n junction, that's the only variable that affects electric field, really, other than the voltage, all right? Turns out it's not. Doping concentration is a very weak thing here. And the problem with scaling of the device is because we scale these things. Okay? Yes?
It seems like it would only be the square root difference, though. Like if you made the argument that L is impacting VD sat, and N sub is impacting VT roughly by the square root.
Yeah, that's what I'm saying. If you're talking about N, are you talking
N
about
sub,
the
it seems still
N
like,
sub effect?
Yeah, it seems like, okay, square root linear, there's still...
Correct.
by
And
your
as I
argument.
said, therefore, it's not in this first order model, as you can see, right? So it's not a strong effect, okay? Surprise a lot of people. And so don't think the pinch-off region is like a p-n junction. That's not what it is, all right? All right, so to summarize, we now have a model that gives us a yen. You know, if you know L, you know Tox, you know Xj, you know Vg, you know Vd. If you know N sub, mainly because you need to know that to get Vt and T, really, just so that not to confuse you. I'll take this out for you, all right? For you, all right? You don't need Vt, otherwise you won't know Vd set. Is that right? Okay. If you know these things, then you will know Vd, you will know Vd set, and you will know L prime, and that is equal to EM, right? There's no unknown at all. Is that correct? Okay. You know, within the constraint, this is only an analytical model. So if you really want to know EM within 10%, you probably will have to, use some simulator to solve the Poisson equations numerically, right? And but as a general trend, this equation definitely captures all the trend correctly, all right? And it's more than trend; it's semi-quantitative, give you a good prediction of what EM should be. Okay. So that's the EM model. So now we're ready to look at the second phase of this discussion. That is, once no EM, can we then understand device degradation, breakdown voltage, that is transistor breakdown voltage, and I sub, etc., right? Okay. All right, so what are we going to do? So far, again, the still review of that EM model. There's the VD set, if you remember, is related to channel lengths. that, right? And this diagram, sometimes I find it interesting to point out. This emphasizes the point about electric field is a linear function of VD minus VD set. So if you look at the IV curve, ID versus VD curve, you see these two curves, right? You have VG1 and VG2. And if you don't remember which of these two VG would give you a larger electric field, EM, just remember, this is the way to look at it. So if I ask you the question, for a given VD, right? For a given VD now, which of these two VGs will result in a larger EM, right? You can, of course, once go into this equation to look at that equation. You say VD set is function of VG, and you will get a correct answer. But I want you to also look at this graphically, look at this diagram, and realize this is the way you can answer the question. The electric field is always proportional to the difference between this point and VD set. You know, where I use this bracket to indicate that length gives us EM, because that length is the numerator of this equation, VD minus VD set. Is that right? So by looking at this, which is this VG will give you a larger EM, VG1 or VG2? Will VG1 give you a larger EM, or VG2 give you a larger EM for given VD? VG1, is that right? Just because this. So when you look at this current, not only you can see IV relationship, I hope you also see the EM in this figure. All right? So that's what it is. Okay? All right? All right. Okay, then all right. Let's see. Okay, so in this diagram, then let me just go to some way of determining, looking at this L prime more exactly. We have introduced a model for L prime that's semi-quantitative. All right, it's not a bad model. If you want to study this more carefully, there are two things you can do. The easiest thing you can do probably is to do numerical simulation. All right, so let's just stay with that. Later we'll see how we can try to get a handle on this even from experiments. All right, from measurement in the lab. But suppose we do simulation. Now that, of course, you know, just means you put a transistor structure into a computer simulator and you know, specify the oxide thickness, channel length, so on and so forth, and then solve this whole electrostatic problem and get a plot of electric field versus you know, Y. And then you try to read what the maximum Y is, maximum EM is, electric field is that right? If you do that, you can imagine you can construct curves such like EM versus VD. You can do that, right? You just simulate for several different VDs, right? And see what EM is. Is that correct? Now, this model tells us EM should be a linear function of VD. It's okay? And let me tell you that many groups have done the simulation inspired by this analytical model. They have all concluded this linear relationship is followed very well, that EM is a linear function of VD. All right? And several things you can learn from this. One is that if you extrapolate this to 0, you can actually have another VD set. So if you want to use this as a way of determining VD set, you can do that too. But this is not a very good way because measuring EM is very difficult, right? Simulation EM is already it's quite difficult. Another thing you can do with this curve is once you have created this curve by simulation, the slope will tell you L prime. You see that? Yes? Yeah? Now you can repeat this exercise for many different oxide thicknesses, for example. Everything else being the same, just do it for several different oxide thicknesses. And then you will be able to tell by simulation whether L prime is proportional to square root of Tox or not. Yes? Is that right? By simulation now, not by this quasi-2D analysis. Is that right? And you can also test the impact of XJ, test the impact of doping concentration, whatever. Is that right? And when in this case, one student did it. When a student did this, he found this is actually proportional to Tox to the 1/3 power and XJ to the 1/2 power. Okay. Some other reference, I think Toshiba study concluded it's proportional to the TOX to the 1/3 power and XJ to the 1/3 power. Right? So this is kind of the different relationships. So if you think you have more faith in the simulation result, feel free to use this result. But again, the difference between this turns out is not that large, provided you start with a starting point, calibrate starting point. Let's say at a okay, I'll put it this way. I probably would hold this 3 to any particular sacred place. Instead, I would want to allow the 3 to be varied by matching it to either one simulation or matching it to some experimental result. Maybe 2.3 is better. But I would still be willing to use this functional relationship to extrapolate that to what happens to L prime when TOX and XJ changes, right? So we can always calibrate this to a current generation of technology. This was found to be pretty good. Even this was done, years ago, more than 15 years ago now, and that's probably done for about 1 micron technology. So certainly would be interesting to update this to see what number we should use for today. And once we have that, I can tell you whether you use 1/3 or 1/2 is not going to make much of difference for next several generation of extrapolation, and that's usually the clever way of doing engineering work, right? You will never just take something blindly and say it's going to work forever. You're always going to update that based on the latest information you have. And once you updated that, for example, choose a number that matches today's device very well, then you can probably assume this will not change and this relationship will be good for next 15 years, just because the theoretical base for these are pretty good, right? Relationships. So that's the way to use this kind of number. But if you look in the literature, once a few years, someone would update this number and just use that more updated number. Okay? All right. So that's electric field. Now, suppose your concern is the electric field is too high, right? You plug this number in, you find out it's larger than this 4 times 10 to the 5th volt per centimeter that I mentioned in the previous slide as being too high, or simply just by experiment, this particular design is giving you a lot of problem with the high electric field. What can you do to reduce electric field of your device so that this technology will be able to meet all the reliability and things like that? So qualitatively, what are the options you have to reduce electric field in a transistor? How about give me some suggestions? Yeah? Turing, what do you think?
Aside from the obvious supply thing?
Obvious, very good. And the comment is good too. Reducing power supply definitely will work. That's something I think your colleagues will not accept because they say, well, there's the standard power supply voltage, you want to use that, and the performance, so on and so forth. Okay, so let's look harder. What else can we do? Yes? June, please. Okay, speaking to microphone is good.
I think increasing L prime would be better.
Increasing L prime, good. So next, how would you increase L prime? Don't put down the microphone. How do you increase L prime?
I think L prime is looks like the sharpnesses in ideal cases, but I think if we make the EM plot looks like that. Right?
Okay, very, very good. Very good. Not only you gave the answer I was looking for, you even gave me some reason why the answer I was looking for was not adequate and what else you can do. I think we all agree increasing L prime is good. The problem is that the obvious way to increase L prime is to make oxide thicker. And we all know there are several reasons we don't make oxide thick. And also to make junction depth thicker. Now this actually is more acceptable than making oxide thicker. But even this is not good because deep junction hurts the short channel effect, hurts the dipole effect, remember? Okay? Right? Okay. And later we can actually perhaps address why there's this contradiction between hot carrier effects and the short channel effect in a more fundamental way. So as a result, the obvious ways of increasing L prime don't work either. So it seems that we're stuck. But fortunately, in the late 90s, at IBM, was invented a concept called LDD. And since then, this has been standard technology. So all the CMOS device made today has LDD, all right? And it's interesting that early on, some let's say 10 years ago, you still see people using the terminology conventional transistor as opposed to LDD transistor. And that's how people study these two different transistor, LDD transistor versus conventional transistor. I say it's funny because certainly today no one will consider LDD as unconventional, and in fact we don't see any transistor other than transistor using LDD. So what does LDD stand for? LDD stands for lightly doped drain. Okay. Now what is lightly doped drain? Let's just use this as the diagram. Now this would be called, used to be called conventional or non-LDD. Today we can call this non-LDD, sometimes called a single drain transistor. All right. So outside this course, there's probably no need to refer to this transistor without LDD. But just to contrast this against LDD, so we have to talk about it. Let's call this non-LDD device. All right. So the model for the electric field EM that we reviewed today or derived today is for a non-LDD device, right? Okay. We know that it's equal to VD minus VD set divided by L prime. And we can even give this L prime a kind of sort of a graphical interpretation. L prime is kind of the average thickness of this high field region, right? So this is the L prime. Well, mathematically, we know L prime is the characteristic length of this hyperbolic function. That's for sure. But one way to sort of understand why EM is this is really, which is the same correct interpretation, by the way, is that you can draw a rectangle. Height is equal to EM. The length is equal to, or the base is equal to L prime, such that the area of this rectangle is equal to area under this exponential function. And the area under the exponential function is VD minus VD set, right? So if we use VD minus VD set, which is also the area of this rectangle, divided by the length of the rectangle, we'll get EM. So this is kind of a graphical way to understand why EM is equal to VD minus VD set over some effective length of this high field region, right? So one way to reduce EM is to increase the effective length of this high field region. But can we do it in such a way that we don't increase L prime? Yeah, we kind of can. What we do is we kind of give some extra space for the electric field to go in. So let me put it this way. This part is the non-LDD solution. It's what we have done so far. It's the non-LDD solution. Okay, non-LDD electric field and voltage is this part. The assumption in the first case is that this electric field quickly dropped to zero because we immediately entered M plus region. When we're in M plus region, it's like metal, there cannot be an electric field, right? The electric field will be forced to drop to zero. So our solution always forced to zero. But what if this solution is not butted to the M plus region, but instead butted to some kind of M minus region, right? And there's no reason for the electric field to suddenly drop to zero. It dropped slowly to zero, right? And then after a while, maybe M plus will appear. At that point, electric field will suddenly drop to zero. You can do that. Okay? If you do that, what's interesting is that we're not encroaching into the channel. You see, this is our channel. We're kind of encroaching into the drain instead. Is that right? We're not encroaching into the channel. With this high field region, we encroach into the drain. What this means is that we don't have to compromise the channel length modulation. And more importantly, I'll quickly extend this to, we're not compromising with short channel effect. The reason is we're not forcing the electric field, or we're not forcing all the voltage to drop on the channel side. We're allowing some of the voltage drop inside the drain. That's another way to think about LDD. Do you follow what I'm saying? Yes? All right, question?
I mean, it seems like that in the limit you just end up adding too much resistance in series with your channel.
Very good. You know, there's no free lunch, but this is probably as close to free lunch as you wish. Later we can discuss just how much we lose by adding the LDD in performance. You're absolutely right, all right? Yes.
I don't see why you just don't use a smaller VD, because it's like you want to drop some of that VD across that resistor, the new lightly doped drain, but you're just kind of wasting it. Why not just use a smaller VD?
Sure. There are two answers to that. One answer is, turns out it can be shown that for a given VD, using LDD, put it this way, let's say compare those two approaches, either adding an LDD or reducing VD. Okay, comparing those approaches, you still get more ID set, you get more performance by using LDD, can be shown. Okay, but let me give you another sort of easy way out of this question. To say, let's say you're an engineer that doesn't have a control on the voltage. Very often it is the case. You have to design a technology for 1.8 just because the world is running on 1.8 power supplies, right? Okay, and let me tell you, the typical situation is this. Power supply voltage is fixed, okay? And later we can see exceptions to that case. But typically the case is the power supply voltage is fixed. As a device engineer, a company developing its technology at Intel, this is what the goal is. The goal is to get the maximum possible performance out of it and still meeting the power supply voltage. Now remember, in what I'm saying, I didn't even particularly call out the channel length. Okay, the channel length turns out is important because packing density. But whether it's another 200 angstrom shorter or not doesn't change the packing density that much. So suppose you actually can satisfy that goal of very high performance and good reliability, even though your channel length is just a tiny bit larger than competitors, you still are okay, and you may actually should be considered a winner. But in reality, it's known that in order to get high speed, you want good current and low capacitance. So it turns out channel length is usually very small. So very often you don't hear people state the constraint the way I did, that maximize the performance and holding reliability. People will say they want to minimize channel length and then holding the reliability, meeting reliability. Turns out these two almost are equal statements, although they could be different, but almost. So the problem usually is that power supply was given, and you're asked to design a transistor that can be shrink to the smallest possible transistor gate length and still meet the reliability. So that's another easy way out of why we cannot simply drop the voltage. But the real reason is that actually if you go through that exercise, dropping the voltage give you less performance than keeping the LDD using higher voltage. That's what it is, all right? Okay, so what you end up doing is, by doing this, you end up with lowering the EM, and to the first order at least, not hurting two things, let me point down. Although we kind of use the channel length modulation as the sort of the other conflicting constraint. Actually, a better conflicting, more important conflicting constraint really is the short channel effect. All right, short channel effect, or dipole. Now we all know that if we use deeper junction or if we use the thicker oxide, we're going to have worse dipole effect, worse short channel effect. All right, let me just remind you another way to think why there's this fundamental contradiction between dipole and channel length modulation. Okay, the fact is that all the device design tricks we know of so far before we reach LDD, okay, namely doping concentration and junction depths and oxide thickness, okay, right, or retrograde doping surface layer thickness, everything we can think of, really qualitatively is affecting one thing, that is how long or how short a distance does it take for the electric field to die out, coming from the drain and die out as we move into the channel. Put another way, how deep does electric field penetrate from the drain into the channel? I'm using some new words for you here. Think about that. How deep does the electric field penetrate from drain to the channel. That's what it is. That's what L prime means, or what L means, right? Is that depth. How much does field penetrate into the channel? So if you're just thinking in terms of those words, let's first establish, do we like to see the electric field penetrate deep into the channel for the sake of dipole or short channel effect? Do we want that? No, we don't. We want to hold electric field very close to the channel, to the drain, right? Now, for the sake of minimizing EM, do we want this electric field to penetrate a distance into the channel, or do we want to hold it to a very short distance close to the drain? Now remember, the voltage we want to drop is fixed, VD minus VD sat. So which do we want? Do we want a deep penetration or small penetration? We want deep penetration. That's why there's fundamental problem. So what LDD does is provide a way to break that fundamental problem by saying, let's bring the electric field into the drain side. All right? So it's a clever thing to do. Okay? Yes?
But I mean, I thought one of the advantages was that because of our, I guess it's exponential dependence, we can drop, at least in the normal, not in the drain side, in our conventional area, additional field can be dropped over a very short distance.
Absolutely right.
So now we're not dropping.
Let's all agree with that. If we did not have the LDD, we really like that what we see here. We can drop the voltage over a very short distance. Everything's fine. We don't need extra 100 angstrom to put in the LDD or what. Everything's fine. And if that does not cause any problem, then we wouldn't be talking about this. The problem is if we did that, EM is too large. We have a reliability problem. They have to give something. Now, turns out this is the least that you give. There's not very much you give, turns out, all right? And let's also follow up what Turi just said. So key really is this. All right, so let's use the concept. We want to allow LDT to drop some voltage, right? But we don't want to waste a lot of space in this LDD region. So what's the minimum length of the LDD that you have to provide in order to drop a certain VD? Let's say there's 0.3 volt too large, then we can tolerate for the reliability. How long an LDD length do we need in order to drop 0.3 volt? Now theoretically, the answer is that you want to sort of synthesize the doping profile such that electric field profile is this. It rises exponentially or hyperbolic sine up to EM, and then just because the clever doping profile you choose, the field stays at EM, right? You don't want to drop either, because as long as it doesn't exceed EM, your reliability is fine. If it drops EM, then it's going to need a longer distance to take care of your 0.3 volt. Is that right? So suppose we can find a clever doping profile. Then this will give us answer how long LDD we want. Why don't we just figure that out? So before we go on, and we know just what is the theoretical LDD length, right? What is the EM we said we could tolerate from last slide? Remember? What did we say? Above that, it's a problem. Below that, it's not much a problem. Yeah, I think I used the word example 5 times the force volt per centimeter. 5 fifths volt per centimeter, right? 10 times larger than the E sat. Okay? Maybe I used 3. I don't remember. I'm sorry. I used 3, I think. 3 or 4. Sorry, I was wrong. I think I used 3 or 4. All right? You can always change the number. All right. And I used 0.3 volt as example. All right? That's reasonable, especially with scaling a power supply. Actually, it's only that 0.2 volt that bothers us. Maybe in the future, it's 0.1 volt that bothers us. It's okay? All right. So divide 0.3 volt into this will give us LDD length. Is that right? Will give us this length, theoretical length. Is that right? Yes? All right. So let's see. Why don't you do this and tell me your answer. 0.3 volt divided by 3 times 10 to the 5th. It's going to be a wrong number. That's good. What is it? What did you find? Give me a number, please. 100 angstrom? Yeah. I didn't do the calculation, but I expect to be that, so I'm sure you're right. Okay, 100 angstrom. Okay, that's the answer. So, well, you can form your opinion now, whether that's a too large a price or too small price. I can tell you that did not start this way. It started that we keep talking about 2,000 angstrom LDD or something like that, and there was a lot of question about, it's really good idea, can we afford to do that? But, when we look at this way, no problem. It's just a matter of how hard we want to engineer it. Earlier on when we were using 5-volt power supply voltage, we may want to drop 1 volt, 1.5 volt there. We want a larger LDD lanes, right? In the future, we're going to drop less than that. So it does not appear to be an acceptable cost or price in terms of density, right? We haven't talked about performance yet. Yes, question?
From a practical perspective, is it easy to engineer this ideal doping profile in such a short distance?
It's not at all. But mathematically, it's interesting. I used to give this as a homework. I think in the 80s, I used to give this a homework to solve this. In other words, in your quasi 2D, equation that you set up, on the right-hand side, there's a charge term, right? We assume that charge is independent of y. So you just put a term that's a function of y, and make the left-hand side, which is electric field, which we solved right-hand side. Now you force the left-hand side to be of this constant, right? d dy to be 0. Then you can figure out what right-hand side that the charge as function y needs to be in order for the left-hand side electric field, d dy to be 0. That's all. So it certainly can be done. And turns out the answer is it's a linear function of doping, right? And is it easy to engineer a linear doping concentration profile? It's not easy. Is it too difficult to do something approximate to that? It's not that difficult either. So certainly there's things we can do, all right? And it's a little bit like information theory, that it's always good to know what's the maximum achievable quantity, and then we can work toward that. In reality, turns out very few engineers even know about these kind of limits. It's just a matter of doing try and error, a lot of design splits. But there are guidelines one can follow that will make the process optimization a lot easier. So this is the kind of basic picture about LDD. Questions? All right, how is LDD made? There are more than one way to make LDD, but most prevalent way of doing it is this. What you do is you first etch your gate, polysilicon gate, use that as the implantation mass for the LDD implant, which means fairly light implant, all right? And gradually the doping concentration is larger, so I'm going to say don't use the term 10 to the 14, let's say 10 to the 14th, all right? That's kind of doping concentration, maybe a few 10 to the 14th implant dose, I'm sorry. So you do the LDD implant at this time. And then you do something that is you cover this entire surface with a layer of oxide, deposit a layer of oxide over it. Now, oxide deposition today is very conformal. So what you end up is a picture like this. Okay, after you deposit oxide over this layer, this is what you get. Over the gate region, of course, you get well. Anyway, this is the surface of oxide that you deposit over the entire wafer. Now, the next thing you do is called etching, and particularly we take advantage of something called anisotropic etching. Let me now give you that word, just called directional etching, all right? Directional etching meaning we only etch in a vertical direction. So imagine we etch this oxide. After a while, we end up with second line here. You see that? And we etch a little bit more, we end up with third line, right? Yes? By doing this enough, you will end up with a case like the bottom case. You have etched away all the oxide over the gate, you have etched away all the oxide over the drain, but you still left some oxide on the side wall of the polysilicon gate. Why? Because here we just have a thicker oxide at the beginning of etching. You see that? So what we end up is something called oxide spacer. Oxide spacer. Once we have oxide spacer, then we can use that oxide spacer as the mask for the high dose M+ implant. See that? Yes? So with this, then we end up with a LDD M+. So we end up with such case M+ and M-. Is that okay? All right, Tori.
So it seems like this above that is the poly of the gate, right? So there's gate poly and then oxide. So that stack is thick by the order of what we care about, probably half a micron thick or so. So that the radius of that oxide spacer left, if we looked at this even conformally,
Right.
will be much bigger than 100 angstroms, or even the oxide.
Yeah. So the question is, what determines the length of this spacer? And you use the term radius, and that's because the way it's drawn here as if it's a spherical thing. Actually, today, the typical dimension would be this, all right? The gate would be still several thousand angstrom in height. Let's call it 2,000 angstrom in height as a poly gate, all right? We want an oxide spacer much narrower than the height of polysilicon. And what determines which spacer is not height of the gate, but rather thickness of the oxide that we deposit to begin with. If we deposit a thin layer of oxide, it will look like that. Then after spacer etching, we will have only this thick of spacer. So we can get 100 angstrom of spacer if we want. Okay? All right. So the control is very good, and that's why this is such a prevalent and popular process. It's easy to do, and okay. Important terminology to remember. This is also known as shallow junction extension. And some engineers don't like the word lightly doped because, you know, as scaling goes on, we're gradually increasing this implant dose. In fact, some engineer for a while, particularly Toshiba, like to call this MDD, which stands for medium doped drain. So it's not lightly doped drain. And others like to call this shallow junction extension. And those are all good names. I think they actually perform the same function. Perhaps you know, some individuals would like to put more emphasis on one versus the other. But I think they actually perform the same function. The functions that some people think are different is that there's connotation, LDD, you do that because you explicitly want to reduce the electric field. Whereas when you do shallow junction, you're not trying to reduce electric field, you're only trying to reduce the drain-induced barrier lowering, DIBO. In reality, I think they're all the same. Doesn't matter what you call it. If you use a shallow junction, lightly doped, your EM is going to be dropped, and your DIBO is going to be improved. Doesn't matter what you call it. Okay? All right. You know, unless the doping concentration here truly is, you know, as high as 10 to the 20th or 20 to 21st. The fact is that even the shallow junction extension is still doped at lighter dose, and doping concentration is smaller. In other words, easier to deplete. That's really the question. What we want is a portion that can be depleted easily. Not so much the concentration itself, not so much the junction depths. Almost it's the areal concentration. I don't want to overemphasize this. I hope you will ask me a question during the discussion session, then I can further clarify just what is required to reduce this electric field, all right? Is it low doping concentration? Is it low dose? Or is the shallowness of the junction, or what? What's required for LDD to function properly to reduce the EM, okay? All right, but you can all see the EM can be reduced, yes.
Yeah, I remember there used to be a structure called the overlapped LDD structure.
Yes.
What happened to that? Actually, that structure will show still can reduce the field, but it can also reduce the source drain resistance.
Yes.
Should be a better structure, but
yes, yeah. Yes. Very good question, Jim. I actually remember I have a slide. Maybe I prepared that for next week, but I will. Why don't I just finish the slides I have today? If there's some time left, we only have 2 more slides to go, and then I'll answer that question. Okay, Jim? Yeah, there is a variation to this. Let's first look at the basic. Now look at the variation. This is the basic LDD structure. Question about the basic structure. Okay. So I'm going to stay with space structure a little bit more before we look at variations to that. All right? All right. So if we now follow understand this LDD structure, then we can extend the theoretical model for EM. For non-LDD structure, we have this case. For the non-LDD, we have the equation EM equal to VD minus VD set over L prime. We can interpret L prime as the effective length of the high field region. So if we just take that concept, do nothing else, would be reasonable to write down a new equation, EM equal to VD minus VD set over L prime plus L LDD effective, right? I'll let you interpret what L LDD effective is. It's a mouthful, terrible notation. But what do you think one has in mind when he extend the first equation into this second equation? Right, L prime is the effective thickness of this exponential function, right? So what is the second quantity, LLDD effective? Probably mean the effective thickness of this part of the field, right? Such that if you take the total area, VD minus VD set, divided by this effective thickness, total effective thickness, you end up with maximum field, right? Now, I don't call that LLDD because process engineers already had decided what this quantity should mean. You know, if you talk to engineers, LDD length, they would definitely interpret as meaning this. This is the LDD length, right? And that's reasonable. Is that right? Yes? LDD length will be the proper quantity to use here if we had an electric field profile, the ideal profile that I mentioned earlier. That would be the LDD, right? But in reality, this LLDD effect is always less than LDD, right? Not a full length is used to meet this EM, right? You see what I'm saying? For example, this LDD may be, say, 300 angstrom in length. Whereas if this was my actual field profile, what would you call this LDD effective? It's clearly less than LDD. In other words, the product of the LDD effective times EM will give me this field, this area. All right? So here there's actually a non-trivial concept. It seems that's a totally trivial introduces quantity. This is one non-trivial concept. Non-trivial concept is we're assuming, and this is actually assumption, that this is not a function of voltage. Right? And depending on the doping profile, it may be a pretty good approximation and maybe not very good approximation. Right? But if you think certain linear systems, then well, let me just say, this is approximation, okay, qualitatively. In other words, conceptually, we can say every LDD can be characterized in terms of hot electron effect as being characterized by one quantity called LLDD effective, and that's it. All your engineering about length, doping profile, you know, everything is included here, okay? Right? This may not be a perfect model for, you know, wide range of EM, but certainly for a small range of EM, a reasonable range of EM, is going to work very well. Okay? All right. So this is the way we can then think about, you know, previous model for EM, how to apply it to the LDD. Now the problem with LDD, so the price we pay, and correctly pointed out by Ryan, is that, or maybe Turi made this point, is the one way to think what LDD does is that to model that as two resistors in series with the source and drain, in series with source and drain. We have seen before, a few lectures before, that anytime we have series resistance in the source and drain, we're going to lose the ID set. And I'm focusing on ID set as sort of a representative parameter to represent performance. All right, we know what that means is that entire IV curve is going to somehow be hurt, but let's just say ID set is what we focus on. Certainly will be hurt by the presence of these extra resistance introduced by LDD. Is that right? Okay. Now do you remember between these two resistance, which is more serious a problem for the performance of the transistor? Is RS or RD, or are they equally problematic? RS, because RS causes reduction in internal VGS, and that's why it causes reduction in the current, right? Okay. And RD only pushes the VD set out more. We don't like that either, but this is even worse of a problem. This does both. It pushes the VDSAT out as well as reduce the internal VGA, therefore reduce IDSAT. It's okay? And we even have seen how to model this, right? So if you are now ready to try to do some more theoretical consideration, the potentially what can be accomplished certainly can use the information we have for the minimum LDD length, right? And the second part, which we haven't done, is, as I said, you could do it as a homework to actually find out what kind of profile will minimize that length, right? And therefore what kind of doping density is involved, and therefore what sheet row, and therefore what RS. And in fact, we can even change that homework to what RS will minimize the, what doping profile will minimize RS rather than minimize the length of the doping of the LDD. So those are all interesting things you can do once we know some modeling skills. And by putting those numbers on, we conclude that, again, this is not something that's tremendously of a problem. We do think that's going to, cut down our current by perhaps 10%. And maybe this will creep up a little bit depending on in the future what kind of power supply voltage we need, you see. If we don't need very high power supply, we don't have to try so hard with the LDD, reduce EM, you see that? Then we don't have to hurt so much. But it looks like looking at the recent trend, it looks like we're still only going to be talking about 10, 15% or something like that. So it does appear to be something that we can tolerate, and then you can compare quantitatively with another way, that is actually drop that 0.3 volt with a resistor. Okay, what do you end up with? Well, first of all, those are interesting questions. Not bad idea, by the way, actually. How some companies deal with special cases where they have just special cases, one transistor, they won't hold a particularly large voltage, and hot carrier is a problem. I actually recommend just add an external resistor. It's very good, the solution, no problem. First of all, you want to add a resistor on the drain side, not a source side, number one, right? And then the question is, how much area is going to take for you to add a resistor? So when you think about it, actually LDD is probably the best way to add resistors. So there are certainly things you can do. And by the way, I want to point out, adding resistor and adding an LDD actually still are different in the following sense. This is where Turi is really, I think this is the point Ryan was talking about. That is, the key to not using a lot of space, not of length, to draw that 0.3 volt is to allow a very high electric field to exist in this extra area to put it in. And LDD does exactly that. We'll put a very high field, 5 times 10 to the 5 volt per centimeter. If you try to put that field in a resistor, think about it. Resistor, like a well resistor, forget about the problem of creating that. Just say we use implant to create a resistor. But you think about resistor. By resistor, at least you should imply you're dealing with the ohmic region. It's called resistor, right? In ohmic region, we can never apply a field larger than 3E4, right? Beyond that's no longer resistor. You see that? So just from the length required point of view, resistor will never perform the kind of feat that LDD is doing. LDD is allowing us to drop that 0.3 volt over a very short distance, and it actually does this with, I don't want to hurry up on this, actually even less resistance than, okay, I'm not going, okay. It gives us less performance drop than putting a resistance outside. Now, this then leads us to another concept. The question is, why do we want this resistor on the source side? We talk about LDD as being useful to spread out this VD minus VD set on the drain side to reduce EM, right? Then why do we need this lightly doped region on the source side? The answer is that there's no particularly good reason. There are several pretty good reasons why we want to do that, all right? But if we could eliminate that, then we would have much less penalty on the performance by using LDD. So once every a few years, someone will revisit this issue of the benefit of asymmetrical LDD. The last time actually AMD works with a student here did this 3 years ago. And every time the conclusion is that, yeah, it is going to be better, but the improvement, is this much. So now you have to compare with the cost. So what's the cost? Cost is the process will be complicated. You have to figure out a way to mask one side, right? It's not impossible, but it's cost. And turns out there's also some cost in terms of the design tools. Design tools today consider transistors or symmetrical. You know, you have to now figure out a transistor by understanding the way that the circuit works, whether you put the drain on one side, on the other side, or maybe some cases you want to put on both sides. And so I'm sure a few years later, you know, this will be studied one more time, and at some point, maybe the boundary condition changes enough that will be worthwhile to do that. This is what I mean. You know, that's all you can do as an engineer. You know, at a given point, you see, this is a starting point. You can, based on your understanding of the theory and physics, and extrapolate to say what is worthwhile to do that. And if things really start to change significantly from today, then that exercise will have to be done again. So far, every exercise end up with the paper, by the way, always says, yes, worthwhile doing, didn't quite emphasize the but part. The but part comes what we know what actually happened, that is, no one has done this in reality. Right? So we know the but part is that it's just not enough to justify the trouble. You have a question, Turi? That's it.
Just wondering, on that slide, is that a drawing error that the LDD is underneath the gate?
Very good. So this kind of leads to the question Jean was asking. So, and this is the last slide. So therefore, why don't I just answer the question a little bit and answer both questions. All right. The question is, in fact, I'll use this so that you can compare. Question is, here I drew the LDD region totally under the gate.
You drew it in your hand diagram also on the last page.
Right.
So
in the previous diagram, I drew it sort of just by illustrating the method of fabrication, right? Method of fabrication ended up a picture that more looked like this. Okay? More look like that. In that case, the LDD is outside the gate. All right? So this we will call full overlap. This is what Jim was asking earlier, meaning all the LDD overlaps the gate. This we will call, let's call zero overlap. It what happened to be edge, right? In between will be some in between. Okay. First answer is these are hand drawing, hand sketch, and the second comment is that in reality, of course, it can be anywhere depending on your technology, how long the spacer is, how much thermal diffusion you use. All right, can go all the way from here to all the way here. You can even have the M plus overlap that. By the way, that's what full overlap means. Even M plus overlap the gate, right? Starting from M minus barely overlapping the gate to M plus even overlapping the gate. So all is possible. And in reality, engineers often just try different ways. You know, more experienced engineer may remember what I did in the last generation, what I learned, you know, or some theory. I have read some papers, therefore I won't go that direction. Otherwise, engineers may very well just try their different ways and then see which will give them the best performance, best reliability, and what can meet the goal. Now, turns out what people have learned is that this has some particular big problem, and there's no time to get to that, so let me just end that. We can talk more in the discussion if we want. And so the trend tends to be more along that direction. And it doesn't necessarily mean it has to be like that. It might be something in between closer to this. In other words, there's some reason that you don't want to really pull the LDD out, although doing so really give you the minimum overlap capacitance. It's for this reason, it's very tempting for engineers to try to design the device this way. But from the hot carrier effect, high field effect, the consideration turns out this gives you lower electric field. Not quite so much lower field, give you better reliability. So as a result, there's this trade-off. Okay? So, Jane, to answer your question, what we actually get today, in my opinion, is close to full overlap. But how to get there is mainly just by you don't use very thick LDD spacer, and so that the diffusion from the M plus almost we cannot almost cannot avoid M plus diffusion to come in, even though we use very little annealing temperature and time. That's still significant diffusion, as you know. We can almost not avoid it. So in my opinion, this is really closer to what the practice is today.
But when you consider for the super halodoping, it looks like the halodoping is inside the channel, while the LDD structure is, source drain extension is just outside.
They both are. again, this is all hand drawing. Easy way to draw hand drawing is to draw this way. Say the halo will be like that. But in reality, halo can be like this as well. That's not a problem, okay? Pardon me? Exactly. So halo doping always use large angle. Okay? And there's also diffusion involved. Let's not to forget about that. They all involved. All right. So let's take a break here and come back in 7-8 minutes. Okay?